Hello everyone, welcome to the fourth session. Let me, as I promised you last time, let me present a few examples of topological spaces. And to begin with, let me just recall the definition of topological space and a few remarks. So let us begin. So recall, let X be a set and tau be a subset of power set of X, okay, and tau be a subset of 2 to the power X. Then we say X tau is a topological space and tau is a topology on X. If, when, it should have three properties. More or less three, right? So what should be the first thing? Empty set and the whole set should be inside tau. So let me write like this. If tau satisfies following. Number one, phi and x should be there. What is second? Closed under finite intersections, right? What it means in symbolic language. If u comma v are in tau, then their intersection is. And what is third? If you have a family of subsets, so if u alpha in capital lambda be a family of subsets of X such that u alpha belongs to where? Tau. Basically I need a family in tau for every alpha in capital lambda or omega. I know my notations and writing is bad, so like whichever symbol you want, some index set basically. So what should happen? Then the union should be there, isn't tau. So these are the three things which we need to check to verify if something is a topology or not. So and one more thing, if you remember, we have defined definition of a open set in general. One you know in metric spaces using balls, but you see that was not in general. So that motivates me to call the members of tau to be open sets. So what is an open set? An open set in X tau, whenever I am writing like this, it's a topological space. X tau is u contained in X, is a set, okay, a set u contained in X such that what should happen? U should be in tau. Basically, members of tau are called open sets. Let me write it. tau topology are called open sets. Let me give you just one more definition. Although it's not necessary at this point, but let's have it here only. So, what is the definition? I want to define something called closed sets. Closed sets. Of course, in a topological space, okay? We say F contained in X is a closed set with respect to, there should be some topology, right? With respect to topology tau on X. I mean, another way to write, you can also write in a compact format like F contained in X is a closed set or in topological space X tau if. So if X minus F, what is X minus F? You are removing points of F from X, or in other words, I guess complement. So this complement should be where? In tau. You see, this is also motivated from the definition of closed sets in where metric spaces. So we are, you see, topological spaces is a big class. Of course, our motivation is metric spaces, as I stated in last session, I guess. So some definitions will be motivated from that thing only. So this is the definition of closed sets in general in a topological space. Okay, good. So let me now begin with some examples. So let us have example, whatever number we can give, 1. Let X be a set and define what I want to define. Let me give a notation also at the same point of time. Tau COF. I will be giving meaning. Don't worry. So what is this set? This is collection. This is, first of all, it has phi. Second thing, it has the sets, all sets U in X, such that X minus U, okay, is finite. That is the condition. So what is my claim? So claim tau COF or COF, whatever, however you want to say, is a topology on X. Let us see how. So let me begin with the first thing. What you should have? Phi and X should be there. Naturally, phi is in tau COF, right? Because we have assumed it. So phi is here. Now, X is also in tau co-finite. Sorry, I have said the name. Okay, I will explain the word later on. So, tau COF, X is also there. Why? Because If you see the cardinality of x minus x, what is this, guys? It's an empty set, so it is 0, which is always finite, right? So less than infinity. Now, let us move on. What is the second property? We have to take 2 and show their intersection is there. So let u comma v belongs to tau. What it means, guys? It means x minus u and x minus v are finite. Right? What you have to show intersection. So let us consider the complement of intersection. So x minus u intersection v. What it is? Something like De Morgan's law. It is De Morgan's law, in fact. It should be x minus u union x minus v. You can verify it, or you might have done in real analysis. Good. Let us see what is. These two sets are same, so their cardinality is also same. This is a way to write cardinality of this set. So this is equal to this. Okay. Now, x minus u and x minus v are finite. So this is also finite, right? I'm not writing it, I'm speaking it, so the logic is clear, right? Because x minus u and x minus v are finite, so this implies this should be also finite. Good. Let us see the next one. So now we have to have a family in tau, COF. So let u alpha in this be a family in tau COF. Basically all u alphas are in tau COF. So what it means? Their complements are finite. For every alpha in index set. Good. Now, what should happen? Let me approach like in a twisted way. So this will imply I want to show that union of these u alphas is in tau COF. So I have to consider its complement. So you and then De Morgan's or like above. So how we can do this? So if you note that, so this means their intersection its cardinality is also finite, right? Why this is happening? Because intersection of x minus u alpha for alpha in omega or omega, this is always contained in each of them, so we can take any one. Right, so this is finite, so this would be, because intersection is inside that. Now what is this, guys? This set is nothing but x minus union u alpha. Again, what we are using, let us write here, De Morgan's law. Good. So this implies union alpha in omega u alpha is in tau. Very nice. Tau COF, suffix COF. So, if you observe what we have done here, so we have shown that this collection will be a topology. Okay. Now let me just name this very special topology. So, remark. Tau COF is known as Co-finite topology. You may ignore this dash also while writing. So, co-finite topology. Why? CO stands for complement and F stands for finite here in the notation. Right? Now, one more thing I want to say about this. You should observe a thing here. I have taken phi, this phi, already inside this tau here. My question is why? Let me just verbally answer you. What if the space, the set X is infinite? If set X is infinite, then what would be the complement of phi? The whole space X, right? So in that situation, if I am not including phi in this collection, then it will not come by this condition. The complement, finite complement thing. Complement of set should be finite. So right, why phi has to be there while defining this topology. I hope this is clear. Let me give you a similar example and I will leave it for you guys to verify that it is a topology. So example, I think 2. Let X be a set and define tau suffix COC. Okay. How I am defining this? This is all u contained in X. First of all, I want phi also here. So all u contained in X such that X minus u is, can you guess? Countable. I hope you remember what's a countable set is. If it is in bijection with natural numbers. That's what the definition of countable sets. And it is inspired from, I think, the region of like the civilizations like Greeks and all, who used to, how they used to count their sheeps. They don't have numbers at that time. So what the people used to do, they used to put a stone in front of every sheep. Once the sheep is gone, they will remove that stone. So you see, it's a kind of 1-1 correspondence only. Okay, good. So you can check that X along with this is a topological space. Fine. And think about the name. What should be the name of this topology? Like in example 1, I am leaving that up to you to like think what should be the name of this topological space. Okay, let me now proceed. I want to give you a simple example That I will also leave up to you guys to verify. But this example is also important. When we will be doing something called separation axioms, we will be using such examples. So your X is, say, a 3-element set, and tau is empty set. Yes. So yeah, empty set and singleton A, and say the whole space. Give me a moment. Okay, yes, this is fine. So what is the claim? X tau is a topological space. Which is known as you might have heard of this. Let me see the spelling, okay? Because I'm pretty sure I will do a spelling mistake. So just a moment. I have to see spelling. I have okay. Sierpinski. So it should be yeah. So what is this? Sierpinski space. I think you have heard this name. If you haven't heard this name, Sierpinski, just this word, search about it. See who is this person, or if it is an English word. I am not telling anything about it, and you will enter a beautiful world of mathematics called something called fractals and related theory. I am just stopping here with this example, and let me proceed further, right? So another example I want to give is this you call as fourth space. Now what is it? Let me define it. So let X be a infinite set. Okay. And X not belonging to X be a fixed point. I'm taking just a fixed point. Of course, I'm choosing this point arbitrarily, so whatever point you want to choose, you can choose. Then, let us define a collection. So it is all open sets U such that, carefully see what's the condition. Two things should be there. One of the two things should be there. So, cardinality of X minus U is finite, or X naught is not in U. Is not in U. So this example has been taken, it can be like at various places, but from where I have studied this first is a book named Elements of Topology, if I am not mistaken. Yeah. It's by Tej Bahadur Singh. I should write professor. He was a professor at Delhi University. Now I think he is retired, and actually this is a very, very, very good book. I will recommend this book, like if you want to explore some good topics like transformations, groups and all. We will come to that point maybe in this set of series. So yeah, let me proceed. Okay, so what is my claim? This is a topology. Okay, which color I was using? Red. Is a topology on X. So let me yeah, let me do a little bit about this, like some maybe let me just verify one property. I will only verify third one. Okay, please verify other properties. Okay, so what we have to do? We have to take a family of subsets in tau. So consider U alpha, alpha in omega, such that, of course, these are in tau. That's what I want. For every alpha in omega. Now guys, there are possibilities, right? Because a set is in tau if it has either one of these two properties. Either the complement is finite or x naught is not in that set. So how to tackle with these situations? We usually make cases. So how to make those cases? Case 1. Let us assume all of this sets satisfies a same property. So say cardinality of x minus u alpha is finite for every alpha in omega. Okay, this you can do. It is somewhat similar to the tau co-finite topology, right? Let me write directly. Sorry, x minus union of u alpha, right? What is the strategy? De Morgan's law. Good. What should be the case 2? On similar lines. Say x naught is not in u alpha for every alpha. So what this implies, guys, if it is not in all, it cannot be in union, right? Okay, so this also implies that the union is there. Where? In tau. What should be the next cases? So that is those are important. Like what we do, like we assume, like say at least one of them is has some condition. So case 3. Or there are various ways to, like some people can also do this thing. Let me proceed with that. Okay, so consider omega to be union of two sets, omega 1 and omega 2, such that their intersection is empty. What I am doing is, it's an index set. The next case would be mixture of the conditions, like some u alphas satisfies that complement finite one condition, and some satisfy that x naught is not in that. So that's what I am distinguishing. So okay, now for alpha in omega 1, u alpha satisfies x naught is not in u alpha. Okay, and similarly for, how should we write, alpha in omega 2, we have complement is finite. That's how we can, you see, the mixture is there. That would be the third case, right? Now, in this case, choose, of course, one who write very specifically can ask this, so let me mention this. Of course, omega 1 and omega 2 are non-empty. Right, only then we can say the mixture is like, it's the mixture. If one is empty, it would be reduced in case 1 or case 2. So choose beta in omega 2. Okay, let us choose this. Now what I want to say is this thing. Observe that intersection of alpha and omega of u alphas is contained in this particular u betas, right? Because this is intersection of all. This would be a smaller set, and this is a bigger set, right? I hope this is clear. Now I think you know my argument. So this is cardinality of this would be what? Less than equal to the cardinality of this, which is finite, and this will implies what? X minus union u alpha. The cardinality of this set is what? Finite. So this again implies that this union is in tau. Why I have chosen case 3? Just I wanted you guys to learn how to write a few things. Like you can all think about this, but when it comes to writing, we have to be precise. So that's why I have done this property third one, and the others that closed under finite intersection and phi and x are there, that you can show. That's not that much difficult. So you see what examples we have done. These examples: co-finite topology, something called tau COC. You have to guess the name. Sierpinski space and fourth space. Now, since I have told you what is open set, what is an open set and what is a closed set. Open sets are member of topology, and the closed sets, a set is closed if its complement is a member of topology. So let me just have a remark about this space, this particular space, what I have told, fourth space. So remark, Number one, singleton X is is both closed and open, and open in where? Fourth space. The space which I have given you here, I am considering the same. X is an infinite set and this is the condition. Okay. For every X in X minus singleton X naught. Okay guys, let us see why. Now, X naught is of course not in singleton X, right? So this means what? Singleton X is open. Good. Now, let us see why this singleton X is closed. So what is the complement? So if you take the complement of singleton X and then you take its complement, okay, what is this? Singleton X only, right? So what this implies? This implies that this thing, this set X minus singleton X, its complement is finite, right? So what it implies? This is a open set. So what it implies? X minus singleton X is open. So you see, by definition of closed set, what are closed sets? Whose complements are open. So this implies singleton X is closed. This is happening for every X other than X naught. That's what I wanted to say. And another remark about the same space. Or let me for a moment have this one only, okay? Or let me ask you like a question. What about singleton X naught? What you can say about this? Okay, singleton X naught. Is it closed? Is it open? Or is it none of them? I mean, right? There can be various situations. So you can verify this thing. And let me end this session by this example of fourth space. I want you to verify this one, example 3. Since I told you it would be this one, important when you study separation axioms, as well as this example 2. These are very standard and important examples we will be seeing as far as we will continue. So let me stop for now. Thank you for your attention.